Good morning, students. Today we will discuss theorem related to quotient module, and then we will discuss homomorphism and its examples. So our first theorem is, let a module M over the ring R and N is its submodule. Then we are to prove that the submodules of the vector module M by N are precisely of the form of A by N. Here A is some module of M containing N. So first of all we will have to define A, that should be some module of M that should contain N, and then we will form the sum module of vector module which will be A by N. So to prove this theorem, let us take a sum module of the vector module M by N, and we have denoted it by X. Now let us define A, the set of all those elements of M such that the quotients formed by them belongs to X. Set of all those X belonging to M such that X plus N belongs to X. Now according to the requirement, we are to prove that A is some module of M containing N. So first of all we prove that N is contained in A. So let us take an element X belonging to N. Because X belongs to N, so the quotient X plus N will be same as N. Now N is the 0 element of X, so that will belong to X. So X plus N belongs to X. And from here, by definition of A, if the quotient X plus N belongs to X, then the element X belongs to A. So we have proved X belongs to A. So X belongs to N implies that X belongs to A. So we can say that N is contained in A. Now, to prove A is some module of M. So let us take two elements x1 and x2 belonging to A. By definition of A, the quotient formed by x1 and x2 that will belong to X. So we can say that the quotients x1 plus N and x2 plus N belongs to X. Now because X is some module of M by N, so that is a subgroup of M by N under addition. So if we take two elements from X, their difference will again belong to X. So we can say that x1 minus x2 plus N belongs to X. Again, by definition of A, if this quotient belongs to X, then this element x1 minus x2 that will belong to A. So our first condition for being a sum module is satisfied. In the second condition, let us take an element R belonging to ring R, and let us find R into x1 plus N. Now by definition of scalar multiplication in quotient module, this can be written as R into x1 plus N. Now R into x1 plus N is equal to R into x1 plus N, and by definition of sum module, this element belongs to X, and if this quotient belongs to X, then this element belongs to A. So we can say that R into x1 belongs to A. So we have proved A is some module of M containing N over the ring R, and therefore we can say that A by N that will be some module of M by N. Now it remains to prove that A by N that is equal to X. To prove this, let us take an element X plus N belonging to X. Now by definition of set A, If x plus n belongs to x, then x belongs to A. Now x belongs to A, so the quotient formed by x, that will belong to A by n. So we can say that x plus n belongs to x if and only if x plus n belongs to A by n. So we can say that every submodule of the quotient module m by n is of the form of A by n. Here A is submodule of m containing n. Now next we define what is R submodule generated by non-empty subset of an R module M. So let us take a left R module M and S is non-empty subset of M. Then the smallest submodule of M containing S, that is called R submodule generated by S, and it is denoted by the symbol span S. Its elements will be of the form of linear combinations of elements of S. Next we define what is finitely generated module. Let us take M be a module over the ring R. We say that M is finitely generated if there exist finite number of elements x1, x2, x3 and so on up to xk belonging to M, such that M is generated by these elements. Then we say that M is finitely generated module. So finitely generated module means which is generated by finite number of elements, and these elements are called generators of M. And if a module is generated by a single element, then it becomes cyclic module. So we can say that an R module M is cyclic if M is generated by a single element. We have taken that element x here. Here x is some element of M. So cyclic module is the module which is generated by single element. Now next we define a homomorphism of R modules. To define a homomorphism, let us take two R modules M and N, a mapping from M into N, that is called homomorphism of R modules if two conditions are satisfied. First condition, under the mapping which we have defined from M into N, under that mapping the image of x plus y is equal to image of x plus image of y. Here x and y are the elements of M. Second condition, for R belonging to the ring R and x belonging to M, image of Rx under the mapping F is equal to R into image of x. So if these two conditions are satisfied, we say that the mapping F is homomorphism of R modules. Here we are having left R modules in the whole section if it is not mentioned. Now let us see some examples of homomorphisms. First example, let us take a left R module M and N be its submodule, a mapping defined by I mapping from N into M defined by image of x is equal to x. Here x belongs to N. This mapping is called inclusion homomorphism or natural homomorphism. Now let us prove this is homomorphism. So we are to verify these two conditions. In the first condition, let us take two elements x and y belonging to N, and we find image of x plus y under this mapping I. Now by definition of this mapping, image of x is x. So image of x plus y will be x plus y. Now x is I of x, y is I of y. So we have proved image of x plus y is same as image of x plus image of y. So our first condition is satisfied. In the second condition, let us take R belonging to ring R. and x belonging to n. We find image of Rx. Again, by definition of mapping I, image of Rx will be Rx. Now we can put the value of x. X is I of x. So image of Rx is equal to R into image of x. So both conditions for being a homomorphism are satisfied by I. So we can say that I is homomorphism of left R modules, and this is called inclusion homomorphism. Now our next example is zero mapping, zero homomorphism of a module. So let us take M be a module over the ring R, then the zero mapping defined from M into itself, defined by under this mapping the image of every element of M, that will be 0. This is called zero endomorphism of M, and obviously it satisfies both conditions for being a homomorphism. That is why it is called homomorphism, and because it is defined from M into itself, so that is called endomorphism of M. Now our next example of homomorphisms is we will define a homomorphism which gives us projection of n-dimensional real Euclidean space onto its ith component. So let us define it. A mapping F from Rn into R. If we take an element having the n coordinates, x1, x2, x3 up to xn, so this element is an element of Rn, and its image under F we have defined by ith component of this element, ith component of this vector, that is xi. In this way we have defined the mapping F. We will prove that this mapping is homomorphism of Rn onto R. Now to prove this, first of all let us take two elements belonging to Rn. So they will have n coordinates. First we have taken having the coordinates x1, x2, x3 up to xn, and second we have taken y1, y2, y3 up to yn. These are the coordinates of second vector. Now let us find image of x plus y. This is x, this is y. Now by definition of addition, that will be coordinate wise here. So this will become f of x1 plus y1, comma x2 plus y2, and so on, xn plus yn. Now by definition of f, the image of this vector under f, that is the ith component. So from here the ith component is xi plus yi. Now what is xi? Xi is the image of this vector under f, and yi is the image of this vector under f. So our first condition for being a homomorphism is satisfied. In the second condition, let us take an element R belonging to ring R and a vector belonging to Rn having the components x1, x2, x3 up to xn. Now let us find the image of R into x. This is x here. Now by definition, this can be written as image of Rx1, Rx2 and so on up to Rxn. And by definition of f, image of this vector is the ith component of this vector. Ith component of this vector is Rxi. Putting the value of xi, xi is the image of the vector having the coordinates x1, x2, x3 up to xn. So these two conditions are satisfied. So f is homomorphism of R module Rn onto R module R, and this is called projection of Rn onto its ith component. One more example based on homomorphism is, let us take A is a matrix of m cross n order over a field F, and a mapping T from Fm into Fn. Here Fm is a vector space having the elements of the form of 1 cross m order matrices, and Fn is the vector space having the elements of the form 1 cross n order matrices. We have defined the mapping T by image of V under T is equal to VA. Here V is element of this vector space. This mapping is a linear transformation because here F is a field. So here we will call this homomorphism a linear transformation. Now we proved that this mapping T defined by us is a homomorphism. To prove homomorphism, let us take two elements V1 and V2 belonging to this vector space, and we find the image of V1 plus V2. Now by this definition of T, image of V1 plus V2 under T, that is given by V1 plus V2 into A. Now this can be written as V1A plus V2A. V1A, that is the image of V1. V2A is the image of V2. So we have proved image of V1 plus V2 is equal to image of V1 plus image of V2. Now in the second condition, let us take a scalar A belonging to F and V belonging to the vector space Fm, image of AV. So by definition of T, this will be A into VA. Now this can be written as A into VA, that is the image of V under T. So we have proved image of AV is equal to A into image of V. So both conditions for being a homomorphism are satisfied. So these were some of the examples related to homomorphisms. So these are homomorphisms of modules.